Okay, yeah, it's 5 minutes past. I'm going to start now. And today we're going to do theory on von der Malsburg network or unsupervised learning, and also known as self-organization. You'll see why in a bit. Today we're going to do the theory, the concepts. So no coding, no nothing, we're just going to talk through the problem and introduce to you the approach that this network uses and the reasoning behind it. As usual, before we go into that, I just want to make sure that everyone is okay with the what we've covered in the course so far. So last week, you should have submitted your assignment 1. Actually, I extended it to tonight. So you have up to today, midnight now, with some bonus time to submit assignment 1. Let me emphasize, again, this course is not about like, wow, you must get everything right. Actually, if you are pushing the models, likely it is that you're gonna actually have things that don't go right, okay? And really, what I would be very interested in seeing in your assignments is how far you push the model beyond what the assignment actually gets you to do, actually, right? So especially in the last few questions where it's more exploratory. So it's more interesting to me to look at papers or homework assignments that like, hey, there's some interesting things that you've discovered, how you got there, what were your thought processes, how you went through solving those problems, or or how you describe your processes and the problems you encounter. Okay, so all the home assignments are hoping that you can have this opportunity to do that. Okay, so any issues with assignment 1? You're all good. Everyone has either submitted or are good to submit tonight. Okay, then assignment 2 is already open and it will be due in 1, 2, 3 weeks time. Today, next week, and the week after. Okay, and it's similar. We've actually done so much of the assignment last week in the lab. So assignment 2 really should be on your own. You are expanding it further, right? Okay, and so by that token, next week I should be opening up the last assignment, von der Malsburg assignment 3. Even while you are finishing up assignment 2, assignment 3 is there for you. So you can see the overlap and the distinctions with the other networks as well. But of course, the due date will be much later on. Okay, so unsupervised learning. Okay, or in our class, we are dealing with von der Malsburg's paper, von der Malsburg network, or we will be saying a lot of VDM in class today, all right? And also, these concepts are bound together, self-organization is a new set of neural network phenomena that we have not yet touched. That will be quite distinct from the previous, the single layer perceptron, the Hopfield network, and the multi-layer perceptron with the backpropagation. This is quite a distinct departure. Or you might want to say it actually uses those past principles, but uses it in a completely novel way to solve a different kind of problems, all right? And really, when we talk about self-organization, especially, okay, the key thing when we have this notion that something is self-organized, it means that someone else didn't determine it, okay? So usually, if you read von der Malsburg paper, you might get this. I hope it comes across this idea or this very classical argument, and that is whether our neural networks, our biological neural networks, are actually determined that is by nature, or there is some contribution of things that are not determined by biology. So explicitly, DNA versus environment. I'm going to put this out there to you in terms of our current LLM models. Are LLM models determined by code or determined by data? What do people think? I assume you all kind of know how LLM models work, ChatGPT nowadays, right? I hope so, okay? Do you all think it is the code that determines the LLM or the data which it is trained on? Data? Both? Anyone say purely code? I would argue this is like, there is no simple yes or no answer. Yes, I agree. There is something clearly to be said that, oh yeah, clearly is that the code is useless without the data, right? The reason why it works is because it has been trained on the data. That's why it works. However, you could also say like, well, all the data in the world, even without the code, would not have been able to produce this tool in the first place, right? So something about the code took all the data and did something to it. And then you want to say, oh, it's both kind of thing, and then it feels kind of like, well, everything is always both. That kind of argument is so cheap. Okay, but it is beyond just this class and all that. This question is a big philosophical problem, and also maybe our human species needs to be a bit wiser and smarter about this kind of problems. That what do we mean, or what are the implications if we were to say, oh, it is nature, oh, it is nurture, or oh, it is both? Is it just that's all? Or is that something more deeper to it? And I would suggest that there should be. My personal take on it is it reflects something fundamental about the way the universe works. Okay, that people from philosophy background probably would get this a bit more. That there might be something deeper about how the nature part and the nurture part are working together. That it reveals some universal principle that might be very useful, or at least it is interesting. Okay. So anyway, before we deviate too much, because this kind of argument can go along forever and ever, von Neumann-Eibach's network, if you haven't thought about it yet, is actually trying to answer this question. Okay? Because, and how? Because, let me formulate this a little bit more. What this means is that if it is a nature versus nurture debate, okay, what von Neumann-Eibach is trying to show or trying to prove, okay, or demonstrate, is to find out if a neural network can learn behaviors, all right, or patterns that were not explicitly specified. That is, the data table is partial or incomplete, or actually unknown. That's key. Up to this point, we always have an input and some target output. Whether the target output is auto-encoding, where the target output is the input, okay? Or the input and the target output are some arbitrary things, but we want them to, the network to form a reliable or a regular linkage. For von Neumann-Eibach, what the network is supposed to learn is unknown. We don't know what we want or how the network should learn this pattern or this behavior. We just give the network the data, and then we see what the network does. And then from there, we see something, oh, wow, it did something cool, okay? This will, which surprises us as the coder, as the trainer, okay? So that is the unsupervised part. Oops. This is the unsupervised part, the unknown data table linkages, and it is distinct from, so unlike, let's make this explicit, distinct from the hop field and distinct from backprop. Okay, which are supervised then. Okay. What we mean by unsupervised is this, there's this learning, there's the part of the way the network is learned that we didn't specify. It's not supervised. Whereas with the hop field and the backprop, it's supervised. So because sometimes people read the paper and then don't really get like, what do you mean unsupervised? Because in the way you code it, you feel like you are supervising quite a lot of things. You still supervise quite a lot. You still specify architecture, you still specify learning rule, and weights updating. You still specify all of that. And then you feel like, where is it unsupervised? The unsupervised part is something that is to do with the data table. That the data table itself does not give you any target output or whatever. Okay, there is really no such thing in the von der Waals network, which is in contrast to the hop field, which are supervised, right? As I just said just now. And so this is the principle here. Okay, so and let's make this even more concrete. This is the very abstract, vague overall rule. How does von der Waals actually what is the concrete problem that von der Waals was trying to address? And specifically, if you've read the paper V1 or even LGN, okay? V1 neurons are orientation, selective. Okay. Whoop. Whoop. Yeah, this side writes better for me. Okay. V1 neurons are orientation selective or have orientation selectivity. And it can be V1, or you might even say, we know LGN also, lateral geniculate nucleus, even earlier on. For those of you who are not familiar with the neuroanatomy, you have your eyes, okay? And then you have your retina. And of course, it's very complicated, but essentially, your retina have the, light-sensitive cells, okay? And then the granule cells and all that. And then they take input and they go to the LGN, okay? And then from here, it goes to V1 neurons, okay? And you get a lot of these, obviously, right? And then it goes to a lot of these as well, okay? And the thing about V1 neurons is that according to work by Hubel and Wiesel, where they did it on, I believe it was cat. And you should go and look them up. They're very nice YouTube clips of their experiments where they put electrodes into cat visual neurons, and then they show the cat, lines a light bar, and according to whether the light bar is oriented like vertical, horizontal, or whatever, the neurons that they are recording will fire only in a particular orientation. So for example, I'm going to, what this means is, it turns out that, so imagine that I'm now talking about V1 layer, okay? So let's say I have a V1 layer here. This is V1. It turns out that there are what we call, ooh, why it didn't change color? That there are these, okay. Okay, there are these what we call orientation columns, where if you were to put an electrode into, this neurons here, these neurons here, you will find that these neurons will only fire when the light is a horizontal light. And then these ones will fire to, like, let's say like this, and then next like this, and then next like this. Okay, and then actually you get back to this, and then you get this again. So it's like as you go along the plane of the V1, if you were to spread out the V1, actually Brown does a lot of this, right? He has this experiment. If you were able to blow up and expand the V1, and then you probe along any direction, okay, you will find that, hey, this neuron, if it likes this one, its neighbor is going to like a little bit, its neighbor is going to like a little bit, and you see these rotating as you go along one direction. The selectivity for those neurons kind of has a rotation kind of thing, okay? So in this view, what we see is that if you were to follow like that, you will see this kind of thing, but you can also have a top-down view. If you were to, if you imagine that now my camera is cutting into the gray matter layer, imagine I were to look at it from a top-down, on plane. This is through plane. Of the gray matter, okay? Gray matter V1, or V1 gray matter, okay? If we go through it, that's what you see in terms of the functional selectivity of the neurons, okay? But if you look on top of it, what you will see is something like this. It looks as if like there's these separate sections in between. I'm just because of the color, I'm just illustrating it. So it doesn't mean that there are gaps in between the patches. Okay, they are just fully connected. It's just, or they're fully joined together. It's just for me to do the illustration. So here it will be like this. Here would be like this. Here would be like this. And this one might be something like that. And there'll be another patch where this pattern or this mosaic would repeat, okay? And so that it's like there is a central part, and we call these spindles. Spindle organization. That in plane, through plane, you see this gradation. On plane, you see like it is kind of all of the different orientations are centered around some central point. And because what this is basically, it's like as if I were to cut. Right? This is through plane. Got it? Okay? So that is why we're spending so much time talking about this neuroanatomy and neural function, because this is exactly what von der Malsberg is trying to show or trying to explore. Who told the neurons to fire like this? What in the DNA told this neuron that, hey, fire only to horizontal things. Or this neuron, hey, fire to some 45-degree thing. Did the DNA tell the neuron that? And if not, then where did that information come from? Because obviously we observed this behavior. How did it learn this behavior if it was not from the DNA? And because how does the DNA know that in the world there are horizontal vertical lines in the first place? Okay? DNA doesn't know that, right? DNA only knows like, okay, I need to code for this protein or this RNA or whatever, right? Send this out, this signaling, this, that. Right? To the DNA, there's no such thing as horizontal or vertical lines, frankly. Okay? So where did this? Clearly we see the V1 encodes orientation information, but we also know, or we have good reason to suspect that this cannot come from DNA, because DNA, it is hard to imagine how DNA cares about horizontal or any line orientation. So this is precisely why this is that question. Where did this information come from? Is it the nature or the nurture part, and or both? And if so, how? Okay. And this encoding input-output relationship is unknown. We don't really know, information-wise, how to squeeze that information into this neural network so that we get this kind of emergent behavior. Okay? So this is the core of the problem. All right? Any questions so far? I don't want to assume because I'm very embedded into the neural bio stuff, so to me this is like second nature. Okay, it's like classic demo. But not everyone is from the bio background, so I'll just make sure that everyone is okay with this. That this is like, yes, established fact, so to speak. We don't have to argue about this. Okay? Because some people argue. All right? But this is a classic experiment, and this is what we see, and this is the problem that von der Mausberg was trying to show. And this also, I would raise, is a deviation from the LLMs, the ChatGPT that we see. Because nothing in the LLM is interested in this kind of, like, hey, there's some self-emergent pattern that we see in bio. Can we make our models do that? LLMs are not caring about that right now, at least the ChatGPT or Gemini implementations. Okay, so this is a purely neuroscience problem. Okay, all right, so let's carry on with a little bit more. All right. So self-organization. Let me develop the problem a little bit more specifically. According to von der Mausberg, 1973. Yes. Okay. So up to this point, okay, we have always used our to this point. We have only used arbitrary tokens. Okay, so the notion of tokens now takes forefront. I can put anything into a slot machine, and slot machine will give me some result. I just have to put the coin in, the token in, and it will do whatever it was programmed to do, right? And it's always automatic. It's like almost like it's determined because of the way I tweak the system. If my machine, I tweak this, I know that if I put the slot there, then some light will turn on. If I change something, then I know generally that that light won't turn on. It's like I control pretty much how the token operates. And in fact, it's binary. We can say it is non-binary. Some of you have tried floating numbers, float numbers, not binary numbers. But essentially, we are taking it in the sense of the thing that we are trying to so-called model is about being not active versus being active. So, or less active or more active. That is what we are trying to get the network to respond to take in, and also to generate out. Okay? However, okay, but we know that nature, or physics, it seems, in our experience at least, is not arbitrary actually. There is cause. I'm not talking about some religious thing about like God caused everything, or some, some spirit causing things, which is fine. Here, we're talking about cause in at least within the scope of our observation. We have observed that the universe doesn't happen arbitrarily, right? How we are right now and the next millisecond of time was caused by the previous millisecond. If those of you who are familiar, you would know this is Markovian, in that everything that is happening right now came from, as we experience it, and as we can explain it, has something to do with what happened just now. Or, forward thinking, what happens right now will cause what happens later on. Okay? Unless you can time travel and all that, which so far at Space I know we don't have that capability yet. Okay? This is how the universe works. And so we learn this, and we can reflect this in our brain system. Okay, we get that there is cause to explain when we see something. Okay, oh, it is coming from an object. Okay, so take the example. So we're gonna really develop this very fundamentally. Yes? Must be. Our psychology tells us that whatever it is we're seeing must be coming from some object out there. Okay? What defines an object? One thing that defines an object is lines or colors. If you're talking about visuals, okay, visual stimuli. If you're talking about sound, then it's frequency and stuff. But in terms of visual, okay, what defines objects is its lines, its colors. You can argue texture, but I will argue texture is just different kinds of lines and colors at different resolutions. And if you want to reduce further, these are frequency on the EM spectra, electromagnetic radiation hitting retina in a particular organization. We perceive as lines, colors. Pretty much that's it, right? Lines and color. Lines. Lines of different intensity. Okay. So this is the conceptual theoretical arguments there. If universe is caused, so we who are embedded in this universe and have to survive in it, we created this notion that there is causes happening to explain what we experience. Then what an intelligent system would naturally begin to formulate is, well, what are these causes? There must be cause, but what are these causes? And one solution is that these causes are internally, right, objects, right? And these objects are composed of, for the visual system, lines of different intensity. But it's not just that these lines are of different intensity. The lines have spatial associations or relationships. Or, another word, constraints. That the lines are not randomly distributed. The lines are sometimes linked together horizontally, sometimes linked together vertically, sometimes in some oblique orientation. Okay? So i.e., the constraints are that these lines have spatial orientations. Okay? That has meaning. It's not random or arbitrary. Physics, nature has meaning. And our problem for our neural network is we have to derive what is this meaning. Okay? So how do we do that? How does our system do that? And do we do it from DNA? And if not DNA, then what? Something to do with the experience or the external environment. Okay? So these kinds of things, really get me. It's very exciting. I can keep talking and talking about it, right? But in this class, we're going to see how von der Malsburg, it's such a big topic, but von der Malsburg captures it in this one paper and to demonstrate in one specific class of problems, right, how our neural system actually does that. Like we infer, what we are doing is inferring the cause about objects, specifically in the domain of orientation selectivity, and this is just developing the background principles of why that, that's what he's doing, and then why that works. Okay? All right. Some other things to raise up about this thing here, this in plane. Okay, so because von der Malsburg is trying to solve this problem, so he's going back to nature and he's trying to understand, like, okay, so the debate is whether it's DNA or whether it's some other thing, okay? But let's understand the system as we can observe. So perhaps there are some clues that the way the system, that what we can observe about the way the structure of the system can tell us about how it's doing it. If it is not from DNA, then how does it work? So one thing that von der Malsburg noticed or reflected in the paper is that whenever you get, so let's say you have a distribution of neurons here. I'm not drawing this right. Something's weird. Oh, yeah, okay. Hang on. Should be like this, like this, like this. For some reason, I can't draw hexagons today. Okay, there we go. Something like that. Okay. All right. So he noticed that the way our V1 neurons are organized is there are these things called interneurons, okay? Those of you who are neurobio, you know, they are GABAergic inhibitory neurons. That's why the arrow is a T sign, a stop sign. It's inhibitory, okay, rather than excitatory, okay? And he noticed that V1 has these neurons in there. Of course, there are other neurons. There are the excitatory ones. So I can draw, neighboring. Right? There's neighboring neurons that are excitatory. So imagine all the neurons bunched up together. Some of them are excitatory. Some of them are inhibitory. Okay? So and he noticed that the way these things work is that when an inhibitory neuron is active, it will inhibit its neighbors. When an excitatory neuron is active, it will excite some target somewhere. And the result of this kind of thing happening is, and this is the proposition that he gives, all right, is that taking this principle here, or this organization here, he suggested a notion of winner takes all. Okay, in that if I am active, I will inhibit my neighbor. So this is like the more active one single neuron is, the more it will dampen its neighbors. That's what winner takes all means. It's just a graphical illustration. It's not an actual graph, not an actual technical plot. Okay, so it just means that if you tell me what's true, or if you tell me some information, and I think I think this is what's happening, I'm going to tell all of you that you are wrong. Okay, or politically, there is only one president, and the president takes all, right? Correct? There are no 2 presidents or 3 presidents, okay? In a standard system like democracy, that's how it works, right? Okay? Are there other kinds of systems where it's not really winner takes all? I don't know. It's very hard to imagine. At some level, it really depends on how far you can define the level that you are talking about. But the fact is, at the end of the day, it really is winner takes all, most of the time. And it's basically saying that in this network, in how they observe the connection, because there are these inhibition, there are these excitatory negotiations happening, okay? And you observe that, well, whenever there is one neuron that seems to be particularly strong, that neuron seems to win. At least locally, where the neuron has connections, it will be able to inhibit the competing neurons, okay? So at the end, we see who's strongest, who's luckily the most stronger neuron, and that neuron will win, okay? So he's suggesting, based on the observation, that, okay, this is not so-called, strictly speaking, genetically determined. It is genetically determined that, okay, this neuron at first is a stem cell, and then later on becomes a GABAergic interneuron or becomes a glutamate excitatory neuron. So inhibitory neurons are GABAergic, I should mention this, and excitatory ones are glutamatergic. It's not important for you to know this neurotransmitter names, okay? But just so you know that, yeah, of course, these sorts of neurons exist in our brain, and the way they work is such that one excites each other and the other inhibits its neighbors, okay? And he is proposing that yes, there is genetic determination for like what type of neurons you are and the extent to which you are connected to your neighbors. So these are determined. These are hard fixed, right? What sort of neurons you have, where they are located relative to each other, and how far they can connect to each other. These are somewhat DNA determined, okay? But then nothing in this organization determines orientation selectivity, the pattern of the spindles that we see. So, but at least, can we just model this fact that our V1 has these excitatory inhibitory neurons that organize like that, and then we let it see some real physical causes, okay? Give it this input, and then can we see these orientation selectivities come out? If we do, then it means that orientation selectivity is a nurtured thing, comes from the environment, and it's not, that part of it is not DNA determined. The DNA determines the architecture, the organization, but the functional response, just having that architecture doesn't give you that pattern, right? In a million years, if I create an architecture with the inhibitory excitatory neurons and I just leave it there, okay, it's not going to have orientation selectivity. It requires that I still give it some real information, all right? And then I see the orientation selectivity. At least that's the question. That's the hypothesis. And do we see that? Can we do that? Okay? All right? So there's two challenges here. One is that if the universe is random, then there are no lines, no objects. Then even if I have the architecture, I will also still not get orientation selectivity, right? So there is a requirement that the universe itself must be organized before my neural network can be self-organized. Okay? All right. So at this point, I want to let me check. Yes, okay. I won't go into the model per se. We will do that later after the break. But before that, I want to show you this app or animation because it does come up in the von der Mossberg paper. Ising model. Okay, Ising is not a function, it's a name. Somebody called Ising. Okay, came up with this idea that, and you will see how it links to von der Mossberg. That, excuse me, and actually even in Hopfield, I believe. So anyway, so the idea here is that in the Ising fundamental setup is that, well, you've got elements, okay? And elements are connected or organized beside each other. That you and your neighbor and your neighbor and your neighbor they have their neighbors and they have their neighbors. And in an Ising world, okay, there is just one rule. You cannot be in the same state as your neighbor. If you are on, your neighbor must be off. And if your neighbor has the same rule also, if your neighbor is on, then you must be off. So this sets up a conundrum. This is in conflict. Because if I am on and I tell my neighbor to be off, but if my neighbor is on, he will tell me to be off, then what is the settling state? And the answer is, there is no so-called fixed settling state. There is some stochasticity in how the final state emerges. Is competitive. If I'm on and there is some sort of a fixed, you can tweak the parameters so that if I'm on, I will tell my neighbor to be off now and my neighbor will be off, but there is some probability that my neighbor will become stronger because my neighbor has other neighbors that will tell other neighbors to be off or on, and then they will start to switch me off, and if I'm off, then my neighbor can be on. You can see how that kind of dynamically propagates, okay? So this is kind of like what the winner-takes-all thing is how it's working, right? Like if I'm on, I will tell my neighbors to be off. But my neighbors then, when they can come on and then tell me to be off as well, and there is this kind of, it's not just between me and my neighbor. My neighbor has neighbors and I have other neighbors as well. So the collective way that the information propagates creates a very interesting dynamic. And you'll see it very clearly in this simulation. That this is a very fundamental physics model, okay? And there's a lot that we can talk about this. People talk a whole course about this kind of thing, but I'm just showing you as an example. You might have many, many other questions, but we don't necessarily have time to deal with them, okay? But here we have a case where let's imagine that this is a neural network. Imagine that this is V1, okay? And this is the start state, random, that some of these V1 neurons, some of them are on, some of them are off, okay? And if the rule is such that my connection is, if I'm on, then my immediate neighbor must be off, okay? Let's see how this evolves. Do you see that? Let's restart. Okay, let's restart this, and I'm going to do step, okay? Step, 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 step. Okay, then I'm going to start from here. Okay, pause. Compare this to this. right? Can you see how at first it's just static, random. But then somehow there's, after time, some sort of stability happening, right? Okay, so that's the principle here. Ising is a physics instantiation of maybe what the von der Waals is trying to mimic neurobiologically, okay? In the Ising simulation, we know very clearly it is these parameters here, okay? It's part of the equation to say the probability with which I will excite or inhibit my neighbors accordingly in the whole system. So similarly, in the von der Waals network, there are going to be some constraints, which is our activation function, our architecture, our learning rules, and all that, okay? And as we let it run, the network will settle into some sort of pattern like this from the initial static. The only thing is that for our von der Waals network, for the Ising, there is nothing happening. This is just its activity naturally settling on some, it looks like there is clusters, but these clusters don't reflect anything in the external input. There's no input here, okay? But for our von der Waals network, the way it's gonna settle has some reality in terms of some information about the universe, okay? Like, so this is something else that's interesting because there's one very important parameter you will see, temperature, okay? So and this is one of the parameters that you will find, okay? If I make it cold, this is what happens in the Ising simulation when temperature goes down. So ice. At first, this is water, okay? Then I put it in the fridge. That's exactly what's happening, okay? Then I put it on the heat, steam. Okay? So here's something interesting. I do this. You see? If I make the temperature go up and down and up and down, okay? You see something interesting happening? When I vary the temperature like this, the system seems to have some sort of maintain some stability, but also some plasticity, right? And moreover, you can imagine that sometimes some cluster, the information is stuck. But if I bump up the temperature a little bit, it can go over a hump and my information can go to a neighboring cluster. But then I don't want to be too noisy, so I cool down a bit so that then I stabilize the cluster. And then maybe I up it a little bit so then I can transmit. This is what we call criticality, where you are at the edge of when you can change your state or stabilize your state, change your state and stabilize your state. And that is, if you study this, you will see at the critical point, the system is the most able to encode the maximum amount of information, okay? And it has the furthest range of communication between nodes, okay? Because if it is completely frozen or completely in the steam, state, information is just either lost or just kept in one local point, doesn't get transmitted to any other place. But at criticality, there is a maximum amount of transmission, okay? So this is just a side point to show you this really cool app, I think, and can get you to think about, hey, what does that mean for our brain, how our brains work, about some information in some cluster of neurons, how does it get transmitted to other places, and just because I'm just varying the temperature. Temperature means, if you all understand temperature in physics, temperature governs the speed with which atoms or particles move, right? High temperature means my particles can move very fast. Low temperature means my particles move very slowly, that's all, or frozen, okay? So I can vary the speed of the particles, and that changes the way my system captures information or encodes information. Okay, so anyway, just to show you this, because this is a so-called more straightforward physical system, which we are very confident about. We have the mathematical equations. In fact, it is purely simulated by the mathematical models, okay? And the von Neumann is something like this, but from a biologically informed point of view, okay? And the idea is, can we get these kinds of models to show some self-organization? Already you can see this physics one has some self-organization, but our requirement is, can we get the model to show self-organization that is meaningful with respect to the causes that is in the environment, because that is precisely what V1 is, or at least we think that's what V1 is doing. Okay? All right, so this is the setting of the conceptual, very theoretical. We haven't talked about the architecture and the model, right? But this is the goal, this is the mission. And you can see it's very distinct from backprop, from Hop field. Okay? It's a much more challenging one. And you will see that in the assignment, that's why I make it a bit more open-ended as well, because I'm very interested in if people can use things creatively and solve creative problems as well. That's for assignment 3. Okay, any questions about this setup? This theoretical background first. I haven't given you the solution in the VDM, but this is the problem, and this is the theory behind it. What do y'all think? Is this a worthwhile problem? Or it's like, it's giving me a headache and I don't want to think about it anymore?
Kind of blurry, but I think if we start doing our head-on, so maybe it will become more clear.
Yeah. Well, we hope. Any comments? Oh, okay. If not, I'll let you guys think about it, okay? And let's take a break, 10 minutes break, and then hopefully when we give you the model and that it becomes more concrete, and then you will see, oh yeah, where all these floaty notions are being kind of knit together, okay, so that you can appreciate the whole problem even better, okay? So let's take 10 minutes and let's come back at 10:20. Okay, and then we will go into the proper model itself. All right. Okay, guys, let's continue, all right? Yeah, so these are very intriguing questions, and it does go all over, um, but that's the interesting part, and yeah, it's always fun to talk about it. Yeah. Okay, let me see. We're going to go into the model now, and then, or does anyone have other questions about things? Okay, no, if not, then let's go into the model. So now I will switch gears to not so theoretical or conceptual, but more concrete to the technical problem. Okay, so we are trying to, whoa. Okay, we are trying to implement the VDM, which does unsupervised learning, which does self-organization, and the specific class or the formalization of the problem for von der Malsburg was that we observe V1 has orientation selectivity. Okay, so then the question or the hypothesis is, can a neural network have orientation selectivity? Okay, that is the challenge, that is the problem. And what we mean by orientation selectivity is that if I have specifically okay, what we mean by orientation selectivity is that if I were to probe the neurons firing, that it will there will be one neuron that will like this horizontal lines. There will be another neuron, and it is its neighbor that will like oblique, slightly oblique, and then its neighbor's neighbor will like even more deviated degrees, right, of rotations. So that is, in other words, we have cortical columns that lead to spindles, which is what I talked about just now in terms of the neurobiology organization. Okay? So this is the mission. This is the formal hypothesis and question in VDM, is that we observe that V1 has orientation selectivity. Can we make a fake neural network also have orientation selectivity as we observe? And what we mean by orientation selectivity is that if we were to probe in this fake neural network, that we will see somehow something where if I were to probe its neighbor and its neighbor's neighbors, that I would see these kinds of different patterns of sensitivity. Okay? So that is the mission, and can we do that? And the solution, the proposed solution is as such. Give me a second here. The first thing to do, okay, step one, is to create, even though I said that the data table is sort of unspecified, it's, I guess to be more accurate, it is underspecified with respect to the goal, in that there is no clear input-output mapping or states that we want, but there is there still is some sort of a system of input that we want this network to encode or behave to, respond to. Okay, so how do we create this table? This is the tricky part. You won't know how to do it today. You will only know how to do it next week when I show you the implementation. But the input has to be, let's do step A. Okay, so follow me with this. This is traditionally has always been the most difficult thing. At least what von Neumann did is to imagine or set up or start a code to have the input layer, okay? And the input layer is essentially the retina, okay? Mirrors the retina, okay? And his specific instantiation was that I will have 19 units. And with the K subscript, okay? And this is the retinal plane. Or the retinal layer, okay? And it looks like this. It has 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. It's a hexagon with 19 units in it. Okay? And this is the input layer. So it's an AI. It has different states and it has K nodes in it. Okay? So this is the step one is to create a data table, but in creating a data table, we need to first understand the format of the data itself, and the data in von der Malsburg is visualized or imagined as that I have 19 units, 19 input units, but they must be organized spatially like this. Okay? I'm drawing these lines to illustrate. In our previous backprop and hop field, it's always been n-bit words. Okay? Node 1 and node 2 and node 1 and node 3 are arbitrarily associated. What happens in node 1 doesn't have any meaning or is independent from what happens in node 2, 3, 4, or whatever nodes, strictly speaking, unless we do some orthogonality and all that kind of thing. But in the sense that the location of 1, 2, and 3 is the same as the location of 4, 5, and 9, and 7, 8, and 100. No difference just because one is 100 and one is 5 doesn't mean anything. Here, this node is closer to this node than it is to this node, right? This node, these two nodes are further apart than those two nodes. So in other words, if I were to say, it is very important to appreciate this, I will label this node 1, 2, 3, 4, 5, 6, 7, all the way to 19, okay? The different distance R from AI1 to AI2 is less than AI1 to AI3. Or if I were to express it more formally, R of A, I'm going to, yeah, I guess, it's bidirectional in this sense, so I don't need the arrow there. The arrow is meaningless, so like this. Okay? Does that make sense? In other words, the the index k is important spatially. It has meaning. That's why we say a critical distinction that it has meaning, and the meaning comes from spatial constraints. Spatial constraints give this data table hidden meaning, abstract meaning. Do you all get this? This is the critical part. This is the key distinction between this class of networks and the previous two. That there is spatial constraints in the encoding, in the input, and therefore it has meaning. And the meaning is the spatial constraint. Okay. And so we formalize this concept by this sort of instantiation that the distance between two nodes in the input is not arbitrary, and when it is not arbitrary, then it has interval meaning, that one can be greater than the other. That is, that it has value. If it is meaningful, it has value. Okay? Things that are not meaningful have no value, right? Okay? So this is the key part here. Okay, so if we understand that we have our 19 units, and the 19 units are organized this way such that their inter-node distances, so if I were to plot out all the RAI1 to RAIK, right, I will be able to recreate this hexagon, correct? For example, if I were to say this is 1 millimeter, then this is, whatever millimeter, and then this will be, 3 millimeter. If I were to have all the R, so these are the R's, right? These are the R's. If I were to have for every node, and I have all the R's to every other node, and then I go to the next node, and I have all the R's, of that node to every other node, and then so on and so forth, I can recreate this hexagon based on the R's, correct? Right? It is fixed, it is defined because of that reason. Okay, and this will be part of the coding, because you will have to create hexagons. And your hexagons will be defined by the distances of the nodes with respect to each other. Okay, it's very physical. Okay, it's not arbitrary. Okay, so let's go a bit more. So if I have remember I need to do orientation selectivity. So how do these 19 units sort of, how do I use it to encode selectivity? Do it like this. I guess I can still use white. Okay. I forgot how he did. Give me a second. Should I draw? I don't need to draw. I can show you. I draw, it'll take so long. Yeah, there we go. Give me a second. I'm not going to draw it because it takes too long. This is the paper. It's figure, and you have it so you can see it yourself, but it is figure 5. Okay? Where's the, yeah. So this is vertical. And it's 19 units, right? 1, 2, 3, 4, 5, 6, 7, and you count, it's 19 units. And this is the vertical state, S1. This is the slightly oblique state. This is even more oblique, some more, and then horizontal, and then slightly off, then go back, okay? So in other words, S1 to 9. Of the ASIK. 1 to 19. Okay, this is the input table. And you see that this is important to appreciate because now you know that the encoded information is not just about whether that node is on or off, but whether it's on or off and how far is it from every other node, right? Because that totally determines, right, the spatial meaning. Right? If for at all these inputs, what is actually hidden in there, which you don't tell the network, you don't give it any error, you don't give it any self to encode, you just give it the fact that there is these sets of inputs that if you were to focus on any one node, whether it's on or off, it's just one aspect of the information. The other aspect is how far is it from all its other neighbors. This somehow is learned, okay? And in this 9 different patterns. The reason why von der Mausberg used this is that you'll find there's 2 reasons. First, he cannot use a square because a square has bias distances at the corners, correct? Right? In the totality, if you just have a square input, it wouldn't be fair for the corner or the center one because the center node will get more information from the flat sides of the square than it might get from the corners. The corners are further away from the center. So a hexagon is fair in a sense that, I mean, obviously it always will be unfair for the edges, but in terms of distances, it is more equipotent. It is more, equally distributed. So you don't use a square, you use a hexagon for that reason. You could use a circle, but a circle is hard to binarize. So that's why the next best candidate for a simple coding problem is to use a hexagon off. And you'll find that the minimum is 19 units because if I were to have a smaller shape, so let's say you only have this one, right? I can't really do vertical and orientation. The degree of freedom is too small, not so powerful. So I expand it one more layer and I find that, well, then that's 19 units. Okay, so the reason why 19 units are chosen and why hexagon is chosen is a very, very practical way for easy coding. And you don't need more. You don't need another layer. Okay, you don't need an even bigger one because 19 units allow you to have these very comprehensive 9 different states that you can see very visually the orientation selectivity, and all of them have the same number of units active. It'll be 1, 2, 3, 4, 5, 6, 7. Yeah. Always 7 out of the 19 are active. So it's fair. It's never like in this state there are more units active and less than other states. No, all the states have the same number of units active. It's just that the orientation encoded by the relative distances is different. Okay, so this is the data table. So it's, where is my thing? Yeah, okay. So I don't want to draw this. This is too, oops. Okay, you go to figure 5 for the data table. So the input layer has a retinal plane. The retinal plane has 19 units, k units, and it will have, as according to figure 5, 9 different possible states. Oops. 9 different possible states. Okay, that represent all the possible orientations you can get using this 9 different units. Okay, then another component. So you create a data table. Step 2, architecture. architecture. So we fall back to our standard approach. Okay, and this is very tricky. Okay? Get your working memory ready, okay? You have to hold this really in your brain. The architecture looks like that. So I'm just going to draw the hexagon as a symbol here. I won't draw everything, but so this is A, I, K, all right? And it has 19 units. And this is a retinal plane. Okay. And then there will be also a, in von Mausberg, we have a much bigger one. And this is the excitatory layer. Okay, and here we have, this is going to be called A, E, H units. Okay, so we have AI, and AI have, as each one is unit K, and we have AE, which is the excitatory layer, and each unit is unit H, okay, where H is 1, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I forgot what it is in the middle, how many units? I think it was 13. I forget. But anyway, when we actually do the coding, these numbers become important. Altogether, there will be 169 units. Okay, here. Why? It is because so each of the input retinal plane units will send excitatory, each excitatory unit will receive all 19, okay, it's going to get really messy, but okay, it's going to receive all 19 all 19 inputs, and if you were to kind of expand it to all 169, then this is going to be 19 by 169, and in fact, this will be the weights from the input to the excitatory, and it's going to be 19 by 169. The orange lines are like for one excitatory unit, we receive 19 inputs, okay? And the reason why there's this expansion is because, and why is it 169? You will find that 169 is just nice, the minimum required, so that the 19 unit patch has a chance to be propagated at least, or convolved at least, I want to say 3 times, you know, and then still maintain a nice hexagon. You don't want to go more than that because then it's redundant, and you cannot have it less than that because then there will be only like, you know, 1 time repetition or something like that in terms of a nice hexagon. In any case, von der Mausberg used 169 because it has a nice shape there. So it has 169 units, the architecture in the excitatory layer, okay? And it's excitatory because the connections that it gets from its neighbors. Are excitatory. They are mutually excitatory. So we have weights that are, if I'm an excitatory neuron, I get excited by my neighbors. Okay, that's WEE. I also get excited from the stimuli. The stimuli, of course, the input layer sends excitatory signals to me, and my neighbors sends excitatory signals to me as well. Okay, or I send excitatory signals to my neighbors as well. And then, not only that, this is the thing about the architecture. It is also still the cortical plane, so this is the retinal plane, and that's the cortical plane. The cortical plane has an excitatory layer. It also has an inhibitory layer. Inhibitory layer. Right? And it also has 169 units. Okay, and let's call it A, I, Q. So inhibitory layer I has Q units, okay, and it receives input from the excitatory to inhibitory layers. So let's use this one. So I'm going to use this neuron here. We'll excite okay. This one is W, inhibitory to excitatory, and it has also 169 by 169 in size. Okay. And also, oh, sorry, I don't want to confuse you. Please ignore that. It's excitatory to inhibitory. Okay, yeah, excitatory to inhibitory. Okay, and then the critical thing here is that there is also let me maintain the symbol. It's a T sign, which means it is inhibitory, and therefore this is the W inhibitory to excitatory layer, and it's 169 by 169. Yeah, okay. And then by way of illustration, oops. Let me draw this out. This is not exactly how many units, but I'm just wanting to draw this out so that we can have the notion that the distances between these units have unit length r, which we can scale. Okay? And it's important to appreciate that r is unit 1 for the immediate neighbors, and unit 2 times for the next neighbors, and 3 times, and so on and so forth for the next neighbors in a radial way. Okay? This is the architecture. Having this defines the von der Waals-Berg network. Okay, so let's summarize what are the components that we have so far. We have a input layer which has k units. We have A, excitatory layer, which has h units. We have A, inhibitory layer, which has q units. We have the W small I to E, which is the input from 19 to, so this is 19 units, 169 units, 169 units. This is 19 by 169. Then we have the excitatory to excitatory, and this is 169 by 169. We have the excitatory to the inhibitory, which is 169 by 169. And this, then we have the inhibitory, which is capital I, distinguishing it from the small I, which is also 169 by 169. And then we have notions that R, Ri, R, A to RB, okay, has some spatial meaning as well. So we are, in our code, we are going to have at least these variables. 1, 2, 3, 4, 5, 6, 7, 8. 8 things plus plus. There'll be some hyperparameters. But we, in our codes, will need to instantiate these arrays and scalars accordingly. I'm drawing this out as hexagons because the hexagons capture the R, but I'll show you again in vector notation, which you might be more used to when we implement the coding, okay? But first, this is just to show you where the information is, how it's flowing. And so this is traditionally the very most confusing part. Well, there's also other confusing parts, but this is one of the big hurdles. So I want to check, is everyone okay with this step-by-step of the architecture? Show illustrating of the architecture. And you can see you can sort of relate this to what von der Mausburg is trying to do with the orientation selectivity. Well, we haven't implemented it yet, but in terms of like we are modeling the retina and how we have the data input with the orientations, okay? And that therefore this information is being spread out to the V1. So in other words, 169 units is simulated as like the V1 has 169 units, okay? And there's the excitatory I told you about, excitatory layer, and the inhibitory layer as well, okay? And the excitatory layer and the inhibitory layer, I draw it as separate, but really what it is like, as I drew before, they are interdigitated with each other. That in our brain, in our V1, we have in one column excitatory, right? But neighboring also has inhibitory, right? Right? And they are kind of packed, overlaying with each other. Okay, that is true. That's what's happening. So it's more like this representation here in biology. But when we code it, I mean, effectively what we are coding would be that there's these two sort of separable layers in virtual memory, right? But in the brain, they are actually just packed next to each other. That's fine. The critical thing is how they are connected, not how they are coded, okay? And so in this setup, this is the architecture for the von der Mausburg in terms of the vectors, the arrays, and the parameter, the key parameter, which is the distance parameter. Okay, let me show you the vector notation way of doing this so that it might be a bit more straightforward. Vector notation. And that is that we have, this is going to be 19 by 1 vector, and this is AIK. It has a feed forward fully connected to 169 by 1. This is going to be A excitatory layer, H. Okay, let me shift this away so that it looks nicer. Okay. So this is AEH, AIK, AEH, and it's connected by W small IE, which is 19 by 169. Okay, and this one, I drew it too high. It is recurrently connected. This is a new one, okay? Because up to this point, we've only had feed forward or feedback. But here we have recurrent connections, and that is because it is the excitatory layer to itself. Okay, so it has these connections, and then yes, feed forward fully connected to AIQ. Does it have? No, it doesn't have that. Just this. Sorry, let me check something first. Yeah, there's no recurrent for the inhibitory layer, but there's this, E to I, 169, and then I to E, 169 by 169. This is the vector notation representation for the hexagonal representation just now. Yes. Okay, any question about the architecture? Yes?
Why doesn't the inhibitory layers itself?
Right. So you didn't code it that way, and but it still works because what each unit will get is the input, the information of all the excitatory states of the excitatory layer. Then it will inhibit its targets. So it doesn't mutually influence each other, but it is influenced by the excitatory layer. And the excitatory layer already has the recurrence in there, right? The WEE. So the recurrence is already sort of initially captured at the excitatory part. And then that is transferred to the inhibitory layer. And then the inhibitory layer will then inhibit its neighbors, its neighbors in the excitatory plane. So it's not that you can't. There's no reason why I can't have a, but van der Mossberg didn't code it that way. Yeah. And you might say, well, is there something wrong there? Not necessarily, because the recurrence is already there here. Yeah. So, and it is transmitted. You might argue that if you had another recurrence here, that it will maybe augment or speed things up. I don't know. So this would be something open for exploration. Yeah. neurobiologically, I do not think interneurons stimulate each other interneurons. I don't think, I have not read, I don't know if people know, I'm not necessarily, they're always discovering new neurons. But so far in my experience, we know that there are excitatory neurons stimulating inhibitory neurons, and inhibitory neurons inhibiting excitatory neurons. I have not read about inhibitory neurons exciting or inhibiting other inhibitory neurons. Yeah, I don't know, y'all can Google and see if there's been 2026, we already know that, I don't know. Yeah, but just in my experience that I'm not sure whether this really exists. Coding wise, it's not as if you couldn't program it, you could, but then there would be a place for exploration. Yeah. Okay. Any other questions? Where's the output? Yeah. So, see, this is the problem, isn't it? This is not a traditional where you have an input output. So we have an input table, right? That figure 5. Okay. What is the output? So the output will be later when we try this out. We're going to see. Let me use the vector notation first. The output is here. The AEH. Output measure that we want, or the output that we want to evaluate, the output that evaluate for evaluation. As in the backprop and the hot fields, we have a concrete output. And then the evaluation is whether this output is correct with respect to what we want or with respect to the self, right? Here, the output that we want to evaluate is the activity of the excitatory layer, okay? Because we want to ask in these 169 units, okay? If I were to look at this and I'm giving it like, let's say I give it this one as the input, okay? Is it on or off? So I don't need this. If I give it this horizontal line and I ask, is it on or off? Okay, then I look and then the rest are off. And then now I give it a new line like this. Do I find that then this turns off and then the neighbor turns on? And then I give it a new line. Does this turn off? This turn on? So on and so forth. Get it? So the evaluation is the output of the excitatory layer. And what do I evaluate for? Well, I'm going to test it after training. I'm going to test it with the orientation lines. And I want to see if there is the cortical column pattern, that this node only likes this line and its neighbor likes a closer line, but not the exact same line, and then so on and so forth. And I'm going to, look at it every which direction, and I'm going to see if there is this orientation spindles, just like how we see it if we were to look at the real brain data. We can see this in real brain data. Yeah? So that will be the output evaluation. Does that make sense?
So it's both regulated and output?
No, we only care about the excitatory layer, AE. We only care, this is AE, which is 169 units. We want to see these. We are going to train, effectively you'll see, we are actually only going to train this. These are fixed. It's fixed. You'll see. It sounds like a nightmare now with so many things. But actually, everything else is fixed. The only thing that's trained is WIE. You will see. Okay? Which makes sense because it's like, how do I react to input, right? So it must be because my input weights with respect to whatever input are changing, right? So when I give you some input, some new input, then you are going to react in some way, right? So I'm going to change the input weights. And so we only care about how the reaction to the input, right? And where is the reaction to the input? It's in the excitatory layer. Yeah. Okay, does that make sense? Okay, so the way is in principle what we are interested in is, as for evaluation, is this one. So like we have, we gave it different inputs, test inputs, and then we see the pattern of all the activity, whether there's these orientation, selectivity. The other thing that we will look for, in fact, more like we will look for this, is that we will see clustering. That if I give you a horizontal line, this is the pattern. If I give you okay. You get what I'm picturing here? This is what we will see. What is this? This is this. This. Yeah? Okay? So that's the output evaluation. Do we get this? And what is this? This is, if you go and Google, you will see papers have published, right? We see these orientation spindles in mammal brains at least. Okay, so that is the test. That is the target. That is the coding challenge, formal challenge here. It's very different from the others. Okay. There will be, with this basis, we have other metrics. We can count how many neurons are active, how many neurons are active only to one state, not others. We can count and we can do other metrics. But essentially what it is different ways of quantifying the behavior of the AE with respect to the different inputs. Okay? Yes?
I actually want to follow up this question.
Yeah, sure.
So in that case, how do we know whether the model learned it successfully?
Yeah, so one way, there are many ways. One is visual. So when you see it work, you will see that if I give you horizontal lines, these clusters will activate. And then if I change it to a different orientation, it will be another cluster, and it will be neighboring. And you will see these rotations of clusters. And as if they are rotating around some centroid, you will see that. So that visually, you will see that. That's one way. Another way would be I will count. Because the alternative would be, if I have not learned, if there is no orientation selectivity, what is the result? That means if I give you this line, you will be active. This line, you will also be active. This line, you will also be active, right? If there is no orientation selectivity, right? Then my one neuron or most of the neuron will be active to any line. So I can count, for example, let OS be the orientation selectivity index be equals to the probability that neuron EH, is it H? Yeah. EH is active given a a horizontal line, and given all other lines, right? And I encode this probability distribution, and then I can say whether it's selective or not. Because if it is selective, it'll be like this. Yeah. Right, correct? This is selectivity, right? That I only I'm more likely to fire only to one orientation. If I'm not selective, uniform distribution. I equally fire to all different. Okay? Obviously, it might be something more like that. And there might be even neurons doing bimodal, right? There might be that as well. Those could be possibilities. So that's what I mean. We could visually inspect it, but if we want to quantify it, we can create some index. One possibility is a probability distribution, and you can then characterize the behavior of this network. What you mean by selectivity? Well, probability distribution, is it we call this a delta Dirac function, right? Is it 0 for everything, but then just only 1 for a specific case? That is the highest expression of selectivity. Okay? Yeah, it's great questions. Any others? Okay, I'm going to move on, and of course, if there's still, there's a lot of things to think about, but we can deal with it as we go along. So that was the architecture, the data table, the architecture. Now we talk about the activations. And because there are different components of the model, I'm going to talk about activations in a slightly different way than traditionally, okay? First, we will split up the notion of activation and pre-activation. We've talked about this before. Just a quick reminder, pre-activation is this one. And this is the A prime, okay? The A, let's talk about the excitatory units activity. H has A prime of the E of H. This is the pre-activation state, okay? This one. There is the activation state, so this one is the pre-activation state. After you put some logistic, then you get EH. Okay, so the pre-activation state is like when you sum everything first, but it is still computing. It hasn't reached threshold or decide that it has not reaching threshold yet. The activation state is after you have finished doing all the integration, then you pass it through your nonlinear function, then finally you actually get the activation. Okay? All right. So in a second. Okay. So in von Mausberg, the pre-activation state of E prime H, A prime E of H at time t is going to be equals to, I'm going to use matrix notation because the indices are more easier to recognize. E's of i's, to the excitatory multiplied by respectively the AIK. Okay? Of course, it's the weights K, the kth weight towards any unit, plus the hidden unit of its recurrent, so not the hidden unit, H units of its recurrent connection with within its own layer, minus this is why this is key to split up the pre-activation state, because there are these computations that it does first. So the pre-activation state of the excitatory neurons, okay? And this one is this layer, the middle one, right? At the first instance, at times equals t, the pre-activation state of this column is going to be equals to this AIK times WIE plus WEE times whatever AE at that current time, and also WIE of whatever AI at that current time, and it's going to be minus because it's inhibitory. But so this has this component, 1, 2, and 3. So that's what this pre-activation state is, okay? Obviously, to get the activation state, we're going to have the activation function. I'll talk about that later, but let's move on to a second part. This is equation 1, because the second part is the pre-activation state of, obviously, what's missing here is this person here, right? Is equals to the sum of all the excitatory to inhibitory weights of the excitatory unit H. And this is equation 2. Okay, this is the activation, pre-activation equation set up first, all right? And there are some constraints. The constraints are critical, actually, such that WEE is equals to 0 for unit H where R is greater than or equals to 2, or greater than equals to 1, or greater than 1. Okay? This is equivalent. And WIE is also, EI is also equals to 0, and that's why, I mean, you'll see this line, for those of you who can see it already, although it is 169 by 169, it's a very big array. What this will end up with is that everything is 0. Only those around it will be non-zero, right? Okay, so. And it has a real interesting meaning for the network-wise. This is same, okay? So recurrent network is only what we say locally excitatory, right? Because 0 means anything greater than 2 units away doesn't affect me. Yeah? Only things that are within my neighbor will affect me. Yeah? Similarly, for the excitatory to the inhibitory, it is locally excitatory to the inhibitory layer also, right? And this is key. R is equals to 2. For Q, R less than, sorry. Yeah. Where R you can scale R, but let's just say R is unit 1, then you scale accordingly, right? And this is the pre-activation definition that we first calculate before we even apply the nonlinear function at this point, but that's what it is. And you'll see this setup of W means that So for excitatory, only my neighbors, will excite me. My distal units have no influence on this unit, right? Similarly, this motif translates to how it stimulates the inhibitory layer, and the inhibitory layer will only inhibit here and here. Okay, the inhibitory layer ignores 2 units out, but it will inhibit. It will not. It will not be affecting things that are either close or too far away. It will only inhibit things that are 2 units out. Let me express this. More, not 这么婉转，就这样 ，okay. Else 0. Yeah. Okay, so inhibitory units will only inhibit things at 2 units away, and not the immediate neighbor, and not anything more than 2 units away. So that's what that means. Okay, you get it? Okay, all this is obviously in the paper also. He has nice graphics. You can take a look at that. But this is translating it what it means. Okay. What does this instantiate? This instantiates a gating convolution kernel. What is it? S kernels. I have 2 kernels being applied here. The excitatory one, the one in red, the inhibitory one, the one in white. Okay, the one in white is inhibitory, so you can flip it the other way. But these are convolution kernels because it is of the 169. I'm applying this patch at a time. Yeah, I'm applying to my neighbor, but my neighbor is applying to its neighbor, which includes me, but has other neighbors that are not my neighbors, and then so on and so forth. That's convolution. Okay, and you will see, van der Waals network is this is 1978, right, or something, yeah, was doing CNN, convolutional neural network. This is a convolutional neural network. Okay, obviously the current convolutional networks we have are a little bit more sophisticated, but essentially that's what this is doing. So, and this ties into, this is such a nightmare that orientation selectivity comes also because of convolutional kernels existing in our brain. The idea of locality, okay, and this is tied into distance. So convolutions is essentially also the notion of, it stems from the notion of distance constraints. And all of this stems from distance constraints, okay? Such a fundamental concept. Okay, so this is the pre-activation state. What about the activation state, activation function? And as I said, in this evaluation, we only care about AE, right? Well, we have 2 activations that we are caring about. We have one, we want to know AE, and we also need AI, obviously. Okay, and the activation function is going to be ReLU. Okay, what is ReLU? No, ReLU is not. We already have binary ReLU. Okay, binary ReLU is like this. ReLU is like this. Theta, 0, infinity. And it's going to be where Aj okay, so that Aj is equals to max of W AI minus theta and I don't have it here. I have to go and check the sign, the function there. I can't think of it right now. But there's a minimum below. I'll go check it out later. Okay, but ReLU we know anything that's less than theta is just 0, and then anything that's greater than theta takes on the value of that product. Okay. So unlike binary, which is that anything that's greater than theta is just 1, unlike binary ReLU, anything in which anything greater than theta is 1. In ReLU itself, anything greater than theta is the value of that the product itself. That's all. Okay, it's trivial. I can go and remind myself of the actual function. But so this AE is equals to the ReLU of AE prime and theta. There's a threshold, right? And this is ReLU of A I prime. Yeah, theta. And we all talked about this. If you go back to equation, AE prime is this one, equation 1, and AI prime is equation 2. So this is okay. From you calculate the pre-activations. Those pre-activations are then put into the ReLU. Compare it with theta, which is a hyperparameter, and then you will get AE and AI. And AE and AI are used back into equations 1 and 2 as well. You can see the dynamic functional looping. And so we allow this actually, this activation iteration where for any input, I calculate the I start out with randomization, or random weights and everything, so that if I give you some initial input, you will have some responses because you already have some random weights. And then from the pre-activation, I calculate the ReLU, and then the ReLU results get fed back into the pre-activation, and I let this bounce around about 20 times, and then I see what you are at, and then I train you again, and I do that. So this is how you'll see the implementation next week. We're going to see these kinds of waves of input, settling, and then next input, settling, next input, settling. That's how the training is going to go. After I've trained it and then I've kind of satisfied with the training, I can train it more and more times. Every time I will ask, is it showing more and more selectivity, right? First round, maybe it is uniform. Second round, maybe it starts to show something. Third, 10, 50, 100 training, maybe it starts to show the white line, something like that. That's the idea. That's how it's going to happen, okay, for the implementation. So any questions about that? So then that's the ReLU activation function. We have one last part, which is the learning rule, obviously, but yeah. Because one of multiple use ReLU function. Yeah. I suppose your question would be, what if it is infinite? Theoretically, it can go to infinite, right? Yeah. Yes. Yes. And the addressment there will be, apart from the learning rule, there will be a normalization. So I will show you that to you later. Yes. So it's an engineering thing. Von der Mausburg just uses ReLU and then brings it back, not letting it go to infinity, by imposing a global normalization a step. We'll get to that. This one is novel. So in backprop, we had some sort of a normalize or regularization method by having the bias unit, right? Remember? Here, there will be a weights divisive normalization. So it means whatever activity you have in the layer now, well, I want you to shrink it back to some restricted range. So even if it's ReLU, it will never go to infinite because it will always be divided by the relative contribution of the layer. Yeah, you'll see it in a minute. But why von der Maus would just use ReLU in the first place rather than the sigmoid? I don't know. That was just the implementation. The fact is, it works. So, yeah. You could try with sigmoid. I would say sigmoid is more neurally plausible, right? You could try with sigmoid and see how things go. Any other questions? Okay, if not, then we'll move on to the next component, learning or updating function. Okay, and as I said, most of the weights are actually fixed. R of H, yeah? Right, if the weights between these two units, H1, H2, is greater than 2, right? And von der Mausburg says, please make the WEE weights 0.4. Equals 1, neighbors. Meaning, you don't have to train the recurrent excitatory weights. Just make them 0.4, please. I don't know, okay? Feel free to, when you have created your network and you're not satisfied with this thing, yes, go and break it, go and change it, okay? But of course, he says that he's done it, he says it works, try it out first, make your network work first, then after that you break it, okay? But this is the stipulation, okay? EE weights are 0.4 for immediate neighbors, 0 otherwise. So you get a 169 by 169, the diagonals are all 0.4, and everything else is 0. And it doesn't excite itself, obviously. So to itself is 0, and then to the diagonals, immediate off diagonal is 0.4s, and everything else is 0. That's what it will look like. Let me illustrate. It'll be 0.4, 0.4, 0.4, 0.4. 0, 0, 0, 0, 0, 0, 0, 0. That's what the array will look like. Okay? WEE will look like this. Okay? And then similarly, what was it? 0.3. So in other words, instead of 0.4, just swap it with 0.3. That's all. And that's for the excitatory to inhibitory layer, that one, okay? And then, obviously, we have this one, and the inhibition is if okay, it's think of this as the genetic determined part. I guess that's what I would suggest to you. The DNA has determined how much, DNA, as we said, DNA has determined two things. You can, DNA determines whether you will be inhibitory or excitatory neuron, right? The stem cell differentiating, okay? So your whatever DNA signaling things, biological signaling things happening, the DNA or the biological part has determined that you are an inhibitory neuron, you are an excitatory neuron, okay? So that is part of the determining thing. DNA also determines, as an excitatory neuron, your effectiveness in this person is 0.4 because you are a person who has this much dopamine neurotransmitter compared to someone else who has less dopamine receptors, let's say, okay? Or GABAergic receptors, more or less. All this is maybe that part of the DNA part, okay? So just think of it that way. Of course, you can say, well, you know, I can, that might also be susceptible to the environment, like how much dopamine is, I can do LTD, LTP, I might have stronger synapse or weaker synapse as a function of my experience. But yes, those, you see, those modulations come from experience or what we call activity-dependent regulation. Here, let's just assume that, well, let's just say that part has been equalized first. Let's simplify the model to just say, well, we have this part that is genetically determined, and then there's going to be a part which comes from the experience part, which is the only thing, the only weights that we want to learn are the input to excitatory unit weights. That this is going to be updated from the previous weight plus, and this is the interesting thing here. See if you recognize this form. It's the pre-activation state, okay? So it's the prime there. Okay. The eta is the learning rate, same as in backprop, okay? But look at this form. The input, AI is the input, and AEK prime is the excitatory layer's pre-activation level, okay? And this is product together, and then that is added to the previous weight to give you the new weight, okay? This arrow means that this is updated from that. Sorry, the original weight becomes this plus that, okay? So that's the updating. It's the same thing as saying the update. But it is updated by that expression. Can you recognize this expression? AE times AI. Does it look familiar? What does it look like? Huh? From the yes, Hebbian learning. Exactly. Very good. Yes? It is two vectors, dot product. So to the extent you which you agree, you added it. The extent which you disagree, you don't influence the weight. So in other words, we have the Hopfield network coming in here again, the Hebbian rule coming in again. all right? But this is not the key part. It's not trying to emphasize the Hebbian learning, but it's using Hebbian learning to update the weights, but embedding that in the VDM architecture with the lateral inhibition and the constraints of the spatial distances. Okay? So in other words, if I'm a neuron that randomly I already like horizontal lines, right? Then to the extent that the stimuli has a horizontal line that I agree with, I am going to tell those retinal neurons, hey, I like you, you're my friend, right? Please, next time, please tell me more, okay? But those vertical people, not my friends, right? I don't want to listen to them, so I don't care about them. That's one aspect of the learning. But plus the fact that because remember, how I like something is also a function of all my neighboring signals telling me that, hey, I'm also your friend, you should listen, or those inhibitory people are telling you, no, you should just be quiet, something else is happening. And some negotiation is happening until I settle onto what do I really like. Do I really like horizontal lines? Or maybe based on what other people are saying, I should be liking something more oblique or vertical lines, right? And over time, I'm going to stay to my idea or change my idea. But if I am someone who is very strong, I really, really like horizontal lines, I am going to be very influential to tell my neighbors that you guys should know that horizontal lines are the most important things in the universe, right? And then you guys should just shut up, right? But then somewhere in another place, in another country, will think that maybe vertical lines are actually more important. And they are going to insist that, everyone else should shut up and they should be listening. So this is almost like politics. So that how things go, which is essentially what neural networks are actually. So how these things negotiate, you end up getting what? You get states, countries, or cities and towns, which is what these clusterings are. Okay? And all through learning rule using still Hebbian principles. So there's a notion of self in there, okay? Self-encoding, auto-encoding, but negotiating with other selves according to some constraint of how much influence I might have with my neighbors, or no influence at all. Okay? How's that so far? Okay? Yeah. This is very exciting to me, all these kinds of things when you think about it, okay? It's very intriguing. Okay, the last part is the new part, which is normalization, which I feel like, I don't know, so if he had used sigmoid function, maybe it wouldn't be so critical, but I would have to say in our brain, we might also actually do have, that it's not just an engineering thing, that our brain might have normalization mechanisms as well, in a sense that a neuron might want to be active all the time, but there is a hard constraint in how many times your neuron can fire. What is the hard constraint? Is energy. Yes? Your neurons cannot infinitely fire. It will burn itself out. It will die. So normalization might be something like that because of the available energy in the neural storage or the extraglial cells which store a lot of the energy. Okay, that might be the normalization mechanism. In fact, we have some evidence for that the extraglial cells, not the neurons, the other cells beside the neurons, they store energy, but they don't just passively store energy. They seem to have activity that smoothens out what the neurons are doing very fast. The glial cells are dampening it. That might be the normalization thing. So there might be some real thing happening here. And by dampening it, it is some sort of a, no, don't go too crazy. We only have this much money. So you can't be spending it all like that. You have to maybe recalculate all the bigger picture here and only spend this much. You will still be able to achieve what you want. You don't have to spend so much money to do that because we are regulating things, okay? So that's the way I see it. So normalization might be a real thing, not just a engineering trick because of the ReLU. So, and how is it done here? Well, remember, the only weights that are updated are the input to excitatory weights, and we can say KH here, right, is equals to so this is not the final weight, this is just the pre-updating weight, right? So the final weight is the pre-updated amount this is the expression given in the paper. The S here is just a scalar number. It's not the state index, okay? It's different. In fact, let's just call it $sign. KH. I think this is the IE also, yes. All the existing IE primes. And S big S. Now let's big S be the states, number of states, and let small s be okay, I'm going to make this fun. Sorry, bear with me here. This is cash. That is $sign. Okay, it's just symbols. So I mean, how many cents you can spend depends on how many dollars you have as your bank capital. And it is a constraint of energetic constraint, like how much you can see in this expression, right? So that the total, let's say you have some total amount and some portion of it is used so that you can adjust the contribution of the whole layer activity. Okay, this part is all the weights currently. What are their activities? I sum it all up. What is this specific weights ratio? Okay, you put this here, right? This is the ratio of this unit with respect to all the total unit. Then, but this unit, if I were to magnify it 19 times, as if all the units were the same as me, right? Then divide by the actual total number of units, what is the ratio between these two quantities. Then adjust it by this scalar, and in von der Mausberg, the $sign, the S, in his paper he uses S. Here I'll use $sign. The cap is 0.25, or the hyperparameter is 0.25. 0.25 means that this is going to be 8. Yes? So it means divided by 8. Why? It's a hyperparameter. I don't know. Maximum, because remember, it's a random number. So you will be at maximum 8 times less by the ratio of your hypothesized total activity relative to the actual activity. That is what this expression will do. So this is the normalization. Okay. Is there any other normalization to do? I'm sure you can try other normalization formulas. Von der Mausberg just uses this expression. That is what this equation does. Okay, so any questions about that? He has to do this because otherwise the ReLU will go crazy, right? ReLU will like add up, infinite. So every time this is adding up, and then after that regularize. Adding up and then regularize. That's what's going to happen. Okay, just see if you can visualize how the code is going to work. Pretty much that's what it is. it's really like politics. Right? Government implements policy is going to run, it's going to go its own way, and then how much money you have is going to limit you, and then people are going to like you or not like you, and then start voting, and then factions will happen, and then they'll have policies. It's totally like that. It's political environment of the brain. Okay, so any questions? Those are the components, okay? So we have the data, which are the 19 units having the 9 different states of the orientations, okay? Then we have the architecture, which is the input to the excitatory, to the inhibitory, and to that. Then we have the pre-activation functions, which are taking, how these input and excitatory and inhibitory layers relate to each other for the pre-activation, and then imposing the ReLU nonlinear gating for it, the nonlinear function to it. And then after that, the learning rule, which incorporates Hebbian principles, and then normalization. These are the components of the von der Waals network. And then we, by doing this, we want to evaluate how the selectivity of the neurons in the excitatory layers are going to respond after training, after we give it time to do all this magic. Then we're going to see, hey, does this self-organization of the columns emerge? I think for the most of you, intuitively, you'll probably feel that it will, right? Because of the way it's organized. Yes, but we don't know analytically. We still have to run the simulation to demonstrate that it does. Okay? Any other questions then, final ones? Okay, if not, then that's it for today. Okay, we've covered the theory and the sort of the formalization. Next week, I have the code. We will implement it. I'll go through the code with you. Really, the most difficult thing for the von der Waals part is the hexagonal coding part. Have you all tried to write hexagon? We are all in Cartesian, like x, y, everything is square. When you want to go to hexagon, it's a bit funny, okay? I've already saved you. If you see the code, you will see my hexagon coding there, okay? There are many ways to solve it, but that's one way there. Some people do polar coordinates, where it's heading and theta degree, right? I think, I don't know if I had that version in there, but anyway, there are many ways to do it, but it's not so simple. It's a headache. People even ask, can we not just do it in just grid anyway? Let's ignore the hexagonal problem. Sure, but let's replicate von der Waals first. Then, if you want to do others and you want to apply it to like regular grid system, sure, of course, try it out yourself. And why? Because I hope if you have done your von der Waals thing correctly, you can expand by doing grid system. What can you do? Your photos, your own photos can be your database. You train your von der Waals network to see your photos, which are grid system, pixels, right? Yeah, 600 by 800 pixels. And you see whether the von der Waals picks up lines. You can binarize your photos, right? Zeros and ones. Or you can tweak your model to accept color as well. So it's not just binary, it can be color or different channels. There's so many ways you can go with this, okay? And that network, you can see, like you apply it to real life data, it'll be very fun, yeah, okay? And you can expand from there, obviously. Okay, so that's it for today. It's 12 o'clock, so it's just good. If no other problems, big problems, then let's stop here. Next week, we will carry on with the implementation. And just a reminder, remember to be busy with the backprop, which will be due in 3 weeks' time. And I will be opening up the assignment 3 as well next week, so that you can also be working together with the von der Mausberg network. Okay? All right, thanks. That's it for today.